This week in lab, we'll be synthesizing biodiesel. Bring your best hippie gear, folks. I want to quickly point out that if you're wanting additional clarity on the analytical data sheets, I did record a video in this folder all about kind of refreshing ourselves on NMR and IR spectroscopy. This week, we're doing a reaction called Transesterification. Basically, we're converting one ester to another ester. Hopefully, we all recognize the functional group here as an ester, and all of these are esters as well. What we'll be doing is we'll be taking some vegetable oil, we'll be adding methanol and a catalyst. We'll boil it at reflux, and then we'll end up with a series of products. Our starting reactant, the vegetable oil, that's a triglyceride. If you eventually take biochemistry, you'll learn that this is one of the main forms of fat or lipid. Triglycerides definitely exist in the human body. And we'll basically be chopping oops, I drew that last one in the wrong spot. Basically, we'll be chopping off all of the various arms of the triglyceride. So how does this happen? We'll do a quick mechanism here so we kind of understand what's happening in the laboratory. And I'm going to simplify much of this molecule here for us today, just like it was shown you on the previous page. You see that in the simplified version of the molecule, we've kind of abbreviated these three different side chains as R1, R2, and R3. Generally, in something like vegetable oil, it's a very long carbon chain. Since we're talking about a liquid oil, not a solid, we expect to find some amount of unsaturation or some number of alkenes in the R groups. Okay. Let's do this mechanism. So, our first reactant is the triglyceride. Second reactant is methanol. Now, methanol, not a particularly strong nucleophile. So how might we make it a better nucleophile? Well, that's what the catalyst is for. We add some sodium hydroxide, and in solution, our hydroxide is a pretty good base to abstract this proton from methanol. Then we have a methoxide, pretty strong nucleophile. So we grab that proton, do a little acid base to begin with. Now we have methoxide, OCH3 minus. Great nucleophile. It's going to attack the biochemist's favorite electrophile, the carbonyl carbon. 'carbon. 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 ' Excuse me. Okay, now we have our tetrahedral intermediate that will collapse back down. You know, oftentimes, folks, we're asking ourselves, really, they're both equivalent leaving groups, right? So why would one leave over the other? Well, eventually in this reaction progress, we'll have the rest of the triglyceride leave. Possibly something to think about when you're doing your reaction is how many equivalents do you have? Do you have more of the triglyceride, or do you have more of the methanol in terms of equivalents? And how will these equivalents make the reaction progress? Good question. Let's not forget that in the previous step we formed water. And we can't forget that a catalyst is always regenerated. So we had that hydroxide molecule, grabbed a proton to make water. Well, in this reaction, we're not making water. That catalyst is regenerated. So what can we do? Well, something that we can do, folks, is make a better leaving group. Let's make this part of the triglyceride a better leaving group by adding a proton and regenerating catalyst at the same time. This reaction looks good to go for me. We can collapse that tetrahedral intermediate. Carbon can only make 4 bonds at a time. And look, we have this great leaving group off to the left. And let's see what happens. So, in essence, we've performed a hydrolysis reaction of that bond. Except rather than hydrolysis, we used a methanol and methoxide. And so, folks, you can see that we've cleaved off just one of the 3 arms of our beginning triglyceride. If you look at the number of equivalents of methanol we add, you might see that we have enough methanol to not just cleave off one of the arms of the triglyceride, but all 3 arms. So this mechanism will happen 3 times per molecule. Things to look out for, folks. We made better nucleophiles by using our catalyst. We regenerated our catalyst to make a better leaving group. And finally, ended up with our products. That's the reaction for this week. Let's talk about some of the important points of the protocol. So, I do want to mention that our catalyst this week will be solid NaOH. Sodium hydroxide is corrosive, particularly to skin. So please be very careful when you're using this in your reaction. You'll see that you'll kind of grind it up in a mortar and pestle. Be very careful when you do that. Additionally, you'll see that when your reaction is done refluxing, you'll pour it into a test tube and allow the layers to separate. If I go back 2 slides here, folks, you'll see that you have 3 products that look quite similar, and then 1 product that looks different. These will separate into 2 distinct layers. Take a moment and think about what product will be in which layer. It might be a good idea to look up the density of your products so that you can determine which is which. Additionally, folks, when we're pouring liquids from one piece of glassware to the next, let's make sure to use a funnel. TLC. So this week we'll be doing TLC again. Let's work on making those TLC spots even smaller this week. If you're using solid crystals, really all you need is 1 crystal, folks. If you're using a liquid, really all you need is a half a drop, not even a full drop from a pasture pipette. So be very careful with this. A lot of our spots are still too big. Additionally, check those TLC plates before you put them in the chamber. If the spots are too big to begin with, go ahead, prep a new plate before wasting your time running it and then determining that the plate isn't any good. I was also noticing that a lot of plates were a little bit dirty. So really make sure to hold the TLC by the edges. Do not touch the silica coating of the TLC plate. Any kind of dirt or chemicals that are on your gloves will transfer to the plate, and it will make your TLC plate a little bit worse to visualize. Finally, don't forget to pre-weigh your round bottom flasks this week, so that after you have your final product in them, you can take a quick mass, get the difference, and know how much product you've made. And again, for this part, for transfer into round bottom flasks, if you're not using a pipette, if you're pouring, please make sure to use a funnel. Now let's talk a little bit about our product. So the 3 ester products, that's our biodiesel. Biodiesel, I think, was really big in the news maybe like 5 or 10 years ago. Now I think electric cars are a little bit of a bigger topic. Biodiesel can be blended and used with regular old petrol diesel, like what trucks run off of. If an engine is going to use 100% biodiesel, that engine requires modification. Most of the engines that are in cars or trucks that we're familiar with couldn't take biodiesel. Biodiesel in some circles is thought of as a preferred source of fuel. Why might this be? Biodiesel is often a byproduct of some different manufacturing processes. For example, the manufacturing of corn, soybean, etc. If we're already making this as kind of a byproduct or a waste product, why don't we, think about some green chemistry and use that waste product for good? Biodiesel has uses beyond fuel as well. It can be used for oil spills. Oil spills are particularly harmful for aquatic life. If you mix a little bit of biodiesel into the oil spill, what happens, because that biodiesel is miscible or mixes with that oil, but it has a lower density, it allows that oil to rise to the surface of the water and be cleaned up a little bit easier. So another potentially green use of the reaction we're doing this week. But how feasible is biodiesel, right? Great idea, but is it feasible? Well, the answer is maybe, right? We probably can't do a total conversion to biodiesel over petrol. The US uses a butt ton of petrol diesel. We really don't make that much vegetable oil. And if we were to use an alternate source of triglycerides, such as animal fats, we really don't make that much of that as well. If we combined this, and if we used every single square mile of land in the US to make biodiesel, which, not very likely because I think you and I have to eat food, right? And if these reactions had 100% yield, which, again, not super likely, we would just make enough fuel. So, not super realistic. But, as we just learned in the last slide, biodiesel has more than one use. Finally, folks, our next two green chemistry principles. The first to the top, safer solvents and auxiliaries. So for example, let's make the solvents we use safe. Let's make anything we use for separation safe. Let's make our catalyst safe, right? This week we're using vegetable oil and methanol, both pretty non-toxic materials. Vegetable oil we ingest probably on a daily basis. Methanol is toxic upon ingestion. However, it is not that toxic to work with. Sodium hydroxide. Now, this is corrosive, but in the way we work with it in the lab, and considering we don't use very much of it, it's a pretty good catalyst to use. Secondly, designing for energy efficiency, such as using ambient temperature and pressure. This week, we will not be doing ambient temperature. You'll notice that the reaction is set to boil. Check out the boiling point of methanol, and maybe something to discuss in your conclusion in your lab notebook pages is whether boiling methanol, depending on its boiling point, really is a big use of energy or not. Additionally, ambient pressure. We won't really do this in this lab, but sometimes reactions are done under pressure, really increasing the energy being put into the situation. This week, we're working in the open air, folks, working at ambient pressure. So certainly this reaction isn't using up as much energy as it might. That's all for this week, folks. I'll leave you with your cat meme related to vegetable oil. See you in the lab.